The recent discussion surrounding the interstellar object known as 3I/Atlas has reignited one of the most intriguing debates in modern astrophysics. How well do we truly understand visitors from beyond our solar system? And what should we make of objects that refuse to fit neatly into established categories? First reported through observational data cited by outlets such as News, AZ and Inkle, 3I/Atlas has rapidly become the focus of intense scrutiny due to a collection of unusual features that, when considered together, challenge long-standing assumptions about comets and interstellar bodies. While no single anomaly is sufficient to overturn conventional explanations, the cumulative weight of the evidence has prompted scientists to carefully reconsider whether 3I/Atlas can be described as a conventional comet at all. Interstellar objects are, by definition, rare and difficult to study. Prior to 2017, their existence was largely theoretical. The discovery of 1I/Oumuamua marked the first confirmed detection of such an object passing through our solar system, followed 2 years later by 2I/Borisov, which behaved much more like a familiar comet. These two cases provided astronomers with an initial framework for what interstellar visitors might look like. Against this backdrop, 3I/Atlas stands out dramatically. Its trajectory, physical properties, and chemical composition collectively diverge from what scientists would expect based on both solar system comets and the limited sample of previously observed interstellar objects. One of the most striking aspects of 3I/Atlas is its trajectory through the inner solar system. The object follows a retrograde orbit, meaning it moves in the opposite direction to the planets. While retrograde orbits are not unheard of, what makes this case exceptional is how closely aligned the trajectory is with the ecliptic plane. The flat disk in which most planets orbit the Sun. Measurements indicate that this alignment is within about 5 degrees of the ecliptic, a precision that is statistically unusual for a randomly incoming interstellar object. Typically, objects arriving from outside the solar system would be expected to approach from almost any direction, resulting in a wide range of orbital inclinations. The near-ecliptic alignment of 3I/Atlas therefore raises questions about whether chance alone can account for its path. Timing is another factor that has drawn attention. The arrival of 3I/Atlas placed it within tens of millions of kilometers of Mars, Venus, and Jupiter during different stages of its journey, distances that are relatively small in astronomical terms. At the same time, the object was effectively unobservable from Earth during its closest approach to the Sun, known as perihelion. This unfortunate geometry limited the amount of direct observational data available at a critical moment, forcing astronomers to rely heavily on indirect measurements and observations from space-based instruments and planetary missions. While such coincidences can occur naturally, the combination of close planetary approaches and observational blind spots has fueled speculation and intensified interest in every fragment of available data. The mass of the object's core represents yet another departure from expectations. Estimates suggest that 3I/Atlas has a core mass roughly 1,000,000 times greater than that of 1I/Oumuamua and about 1,000 times larger than 2I/Borisov. This alone places it in a different category from the previously known interstellar visitors. A more massive core implies a very different formation, history, and internal structure. Adding to the puzzle, 3I/Atlas is also moving faster than both Oumuamua and Borisov did during their respective passages through the solar system. As astronomer Jason Wright noted on his Astro blog, this combination of extreme mass and high velocity is difficult to reconcile with standard models of cometary ejection from distant star systems. Equally puzzling is the object's physical behavior as it interacted with solar radiation. Observations conducted in July, August, and November of 2025 revealed the presence of a jet pointing toward the Sun, a phenomenon often referred to as an anti-tail. In typical comets, jets and tails form as solar heating causes volatile materials to sublimate, producing streams of gas and dust that are pushed away from the Sun by radiation pressure and the solar wind. A jet consistently oriented toward the Sun runs counter to this basic expectation. while antitails have been observed in some comets under specific viewing geometries. The persistence and clarity of this feature in 3I/Atlas have made it a focal point of discussion. The fact that this jet was confirmed using high-rise images captured while the object was near Mars lends additional credibility to the observation and rules out simple observational error. The chemical composition of the gas cloud surrounding 3I/Atlas adds another layer of complexity. Spectroscopic analyses indicate an unusually high abundance of nickel relative to iron, as well as an elevated ratio of nickel to cyanide. This chemical signature differs significantly from that of thousands of comets studied within our own solar system, including 2I/Borisov, which otherwise served as a useful benchmark for interstellar comet behavior. Nickel is not unheard of in cometary environments, but the specific ratios observed here are difficult to explain through conventional comet chemistry alone. Such an atypical gas mix suggests either a fundamentally different formation environment or processes acting on the object that are not commonly seen in natural comets. Gravitational interactions also play a role in shaping the narrative around 3I/Atlas. One of the anomalies highlighted by researchers is its closest approach to Jupiter during a 2026 encounter. Jupiter's immense gravitational influence often acts as a gatekeeper for objects entering the inner solar system, altering trajectories or even ejecting bodies entirely. The precise nature of 3I/Atlas's interaction with Jupiter, combined with its already unusual orbit, has prompted careful modeling to determine whether known gravitational dynamics can fully account for its motion. So far, the results suggest that while gravity explains part of the behavior, it does not neatly resolve all observed deviations. Harvard astrophysicist Avi Loeb has been among the most prominent voices drawing attention to these inconsistencies. While careful to emphasize that extraordinary claims require extraordinary evidence, Loeb and others argue that dismissing the anomalies outright would be unscientific. Instead, they advocate for a rigorous examination of every deviation from expected behavior. This approach does not assume an exotic explanation, but acknowledges that the existing data do not align comfortably with established models. In this sense, 3I/Atlas serves as a stress test for current theories of comet formation, interstellar travel, and solar system dynamics. The systematic documentation of these anomalies has been crucial. Platforms such as Primetimer have compiled clear records of each unusual feature, presenting them as observed rather than filtered through speculative interpretation. Data from sources including JPL horizons, high-rise imagery, and various spectroscopic studies form a multi-layered evidence base. The consistency of certain findings across independent instruments and methodologies strengthens the case that the anomalies are real and not artifacts of measurement or analysis. Importantly, the scientific community remains cautious. Re-evaluating whether 3I/Atlas is a conventional comet does not automatically imply that it is something artificial or beyond natural explanation. Nature has a long history of surprising astronomers, and many phenomena initially thought to be anomalous have eventually found explanations within physics once sufficient data were collected. However, the challenge posed by 3I/Atlas lies in the number and diversity of its unusual traits. Each anomaly might be explainable on its own, but explaining all of them simultaneously within a single coherent model has proven difficult so far. The broader significance of this debate extends beyond a single object. If 3I/Atlas truly represents a new class of interstellar body, it could reshape our understanding of planetary